Hi, everybody, and welcome back to another episode of Profiles in Canada, Scouts Canada's web series, where we connect with Canadians who use their talents to the fullest in pursuit of the common good. I'm Kayla Moniz, and today we are here with Professor Art McDonald, the Professor Emeritus at Queen's University in Kingston, of course, close to the First Bay Ridge Group and the First Amherst Review Bath and White Pine Council. Professor McDonald won the 2015 Nobel Prize in Physics for his research into neutrino particles, which are very, very small particles of matter. While Professor McDonald is technically retired, he still does his research into neutrinos and dark matter. And of course, Professor McDonald is also retired from being Scouter McDonald in Cubs, which he was with the first Deep River Scout group, and still has no fewer than 9 Cub cars to prove it. So, Professor Scouter, thank you so much for being with us today.
Oh, it's really my pleasure. I valued the scouting movement myself, and I can see that it's still thriving and doing the same things for young people.
Professor, with every guest of ours who has a personal connection to being a scouter, we start with 5 rapid-fire scouting questions. Are you ready?
Okay, sure.
Winter or summer camping, which do you prefer?
Summer,
Favorite log structure for building a campfire?
probably pyramid.
When building your Cub car, any one of your 9 Cub cars, do you prioritize winning the race or winning the creative competition?
The race, but they weren't my Cub cars. They were my sons, my
Right.
3 sons. So it's three each.
Capture the flag, 7 Cubs, capture the flag, 2 Scouts. Who wins?
Cubs.
And what is your favorite Scout camp?
Site, you mean?
Yes, favorite
Um,
place to go camping.
well, in terms of scout camp, it was on the Myra River in Nova Scotia when I was uh, in my teenage years when I was a scout there.
Lovely. All right, Professor. Now I think we can get to the serious part of our programming. I want to start discussing your research. Um, you looked into neutrinos and dark matter. For our audience, I wonder if you might discuss what they are and why they're so essential to understanding our universe.
Well, neutrinos are very unusual particles. Along with electrons and quarks, they are the three basic building blocks that so far we don't know how to subdivide any further.
I see.
They're
So
produced
are
in
we made of
tremendous.
them? Are we, is that, are
No,
they,
no,
no?
we are not. We are made of the other two building blocks, electrons, of course, that everybody's familiar with, and quarks, which in groups of three make up neutrons and protons that then make up the nucleus of an atom. And around the nucleus are electrons, and that's what gives the atom its chemical characteristics.
Hmm.
Neutrinos, on the other hand, are only emitted in certain types of radioactive decay
Hmm.
here on Earth these days, and in enormous numbers in the nuclear reactions that power the sun. And those are the ones that we studied. And in the process, we were able to understand in great detail how the sun burns. And that's of great value because these days people are attempting to develop fusion power here on Earth. And the fusion that's occurring is very similar to what's powering the sun. By studying the neutrinos produced in that fusion, we understand that those calculations are very accurate, which then is of great value when you're trying to reproduce it here on Earth. On Earth, it's so hot, 100 million degrees in the middle, when you try to build a fusion power reactor, that they have to arrange for the particles that are being emitted, other than neutrinos that go through everything. The charged particles, they bend them back in with magnetic fields, and so they make a magnetic bottle, kind of shaped like a baseball, actually, called a tokamak.
Hmm. Well, you mentioned nuclear fusion. On Earth, at our nuclear power plants, so essentially what gets our electricity, there's something going on called fission. But fission breaking apart, fusion bringing together. Why is fusion so much better? Why is this something that you have looked into as a potential source of new energy?
If you use light nuclei, deuterium being the central one among them, you have an almost inexhaustible source
Wow.
of energy of fuel for the process. Because 1 in 6,000 of the molecules of water that you drink every day is actually not H2O, but D2O, deuterium oxide, where an extra neutron is in the nucleus of the hydrogen atom that makes it the same chemically, basically, but a little bit heavier. So there's an inexhaustible fuel supply. That's one element of it. The second thing is if you have very heavy elements like uranium, it's by breaking it apart or having it fission that you release energy. And that then leaves the parts that have been broken, that it has been broken into, they remain radioactive for quite a long period of time. And you have to take precautions to bury that in such a way that it's safe, which they do. They have techniques for doing that, and it's not a problem for the nuclear power industry based on fission. But you don't have the same problems with the fusion process.
So to confirm then, by looking into neutrinos, this tiny particle that's emitted in the sun, we're able to maybe do some research into how to better power essentially our world by finding better sources of energy with less waste and greater efficiency.
That's right. But we were also interested in neutrinos for other reasons
Hmm.
because they're so difficult to detect. And we had to build a detector the size of a 10-story building. And,
Wow.
and what you see behind me is the set of 10,000 light sensors looking in at a large amount of that heavy water I mentioned
Hmm.
that gave us advantages in terms of studying neutrinos in an underground site 2 kilometers down near Sudbury, Ontario. And we were studying the basic properties of neutrinos because we want to understand how the world works at a microscopic level. And we also want to understand how that came to be. How do we end up with a universe that we see around us today, starting 13.5 billion years ago in the Big Bang? And neutrinos play substantial roles in that. These days, we've moved on in that underground site in a lab called Snow Lab, which is the lowest radioactivity laboratory in the world, to look for one possibility for what the dark matter is in our universe that we don't understand.
Hmm.
But if you look out on a starry night, you will not see 5 times as much mass in the spaces between the stars, the dark spaces, as there are in the stars themselves. And
Wow.
that is what we refer to as dark matter. And it's completely different than any matter that we know about, everything that makes us up and stars and the rest of the universe. So
So
what we're doing is waiting for those particles to bang into our detectors and make a small signal in this lowest radioactivity location that we have at Snow Lab here in Canada.
you mentioned dark matter. I wonder if we might establish what do we know about dark matter? What do we know about what it is, and what are you able to find out through that observatory that you have here in Canada?
Well, we know how much of it there is, how much mass in total there is of it
Hmm.
in terms of how it holds our Milky Way galaxy in its current form.
Wow.
When you look out on a starry night again and see the Milky Way, you see it as a patch of stars on the sky. But that's because you're looking through it. You're looking through call it a cinnamon roll because it's actually a spiral, and you're looking through the edge of the cinnamon roll, and that's your patch of stars. Other galaxies of a similar form, we can see their form in some detail. And what we find is that the stars at the outer reaches are moving so fast that the gravity that would be associated with the glowing matter is not enough to hold it in that pattern.
Hmm.
You need 5 times more of something else that doesn't glow. That's the dark matter. Our experiments, since we know the dark matter is there, and we're sitting little ways out from the center of the Milky Way galaxy, we're presenting very large amounts of material and seeing if those particles, when they bang into that material, actually make a signal. We're looking for the way in which these dark matter particles interact with ordinary matter. And that's our attempt to start understanding what the heck it is, because we don't know right now.
Fascinating. So I wonder then, Professor, obviously you've done such incredible work in the field of physics and the field of astronomy. I wonder if you might discuss how you got into astrophysics. How did you discover your passion for scientific research?
Well, I developed a passion for mathematics with a high school teacher by the name of Bob Chafe at Sydney Academy in Sydney, Nova Scotia on Cape Breton Island. In fact, I just visited there last week
Hmm.
and gave a lecture to the students, and it was quite interesting. I was the first graduating in the first graduating class from that building in 1960. So
Wow.
65 years ago, I was there. I had a passion for mathematics, as did two of the other people in my 30 some student science and math oriented class who also got PhDs. Theirs were in math. I wasn't interested in continuing to study math for math's sake,
Hmm.
but I was very interested in its use in scientific activities. And I went to Dalhousie University in Halifax, and again, it was a professor, Ernie Guptill, who really got me interested in physics in my first year. And so these days I get asked a lot by younger people, how do you choose a career? And I say, well, think about the things that would be fun to get you up in the morning to go and do the work you're going to do. And there are probably a few of them. Find an opportunity to try them out. And that's basically what I did. I went to university knowing I wanted something where I'd be using math in an effective way and see what you're good at. And so that's what I did. And it turned out I was really good at physics. I was getting very good marks. But I also loved the whole question of, you can understand how the world works by using mathematics. I mean, at that point, it was what angle do you point a gun at in order for the bullet to go the farthest distance or the explosive or whatever. But it turns out to be exactly the same when you're trying to study how a neutrino interacts or how an experiment works and so on. It's a nice combination of the world around you and the use of mathematics. So I still have fun every day I get up in the morning. And
That's
that's a nice thing about science.
that sounds like an awesome objective to have in a career. I'll ask Professor, you've obviously been to the mountaintop, the 2015 Nobel Prize in Physics. Was your path linear? Did you ever encounter setbacks? If you did, how did you overcome them? What lessons would we learn?
Well, that's another thing I say to young people, which is um, get along with other people. Because if you have a large collaboration that you're working with, then uh, exchange of ideas, access to many other bright minds is a very worthwhile thing. And that's something, of course, that you learn in scouting as well. Working together to achieve an objective is something that serves you extremely well in life. And that's what happened with me. It was somewhat linear. I mean, I got a degree from Dalhousie, a bachelor degree. Took a year for a master's degree in experimental physics, and then went to Pasadena, California, to California Institute of Technology, which was a fantastic, one of the top 4 or 5 schools in the country, um, where I was taught by uh, very good professors, and so the quality of my instruction continued to go up. Um, I graduated with a PhD from there and went to Chalk River Nuclear Labs, and that's where Deep River came in. That's where we lived, and then was I was there for about a dozen years, and then in 1982 was hired as a tenured full professor at Princeton to continue doing the same things. And so we were in Princeton through the 80s. And then I was involved in this Sudbury Neutrino Observatory project from the beginning. But they were looking for a Canadian leader for the project because the other leader, George Ewan, was retiring.
Hmm.
So I've been here in Kingston since 1989. And fortunately, I had this group of really qualified colleagues who really built the detector. I was given a Nobel Prize for it, but I just try to represent them well in terms of trying to make people interested in the fact that we can understand our universe by doing experiments like this. We can understand it amazingly well these days, and that's a continuing task, which is great fun. So it's fairly linear.
That's fantastic, Professor. I will ask then for a last word. A big focus of this series has been Canada. It's been our country. And you've been obviously working in both the States and in Canada. I wonder, what has Canada meant for you and for the work that you do?
Well, Canada has been first of all, Canada is the place in the world where I feel most comfortable living. I think the sense of values that people have in Canada of being concerned for other people, in addition to working hard and attempting to make Canada a success, is the sort of place I like to live in. Those are the people I like to live around, put it that way. Um, so I'm here. I have 4 children. They all have some of them graduated in the United States, Princeton, but came back to Canadian universities. Our family is firmly based in Ontario. But in terms of the science, we had a unique opportunity in Canada of the availability of this material, heavy water, that is used in the Canadian style of nuclear reactors, and also a very cooperative management for the mine in which we needed to do. We needed to be deep underground to avoid the sort of cosmic rays that create the northern lights,
Hmm.
make the atmosphere glow. We were looking for 1 neutrino an hour with a faint burst of light, and you couldn't do that if you had your whole detector glowing like that. So those two things came together. We had a very good group of scientists from Canada, the United States, the United Kingdom, and everybody worked together for success. But Canada was the logical place to do this. And as a result, by expanding the location underground, we now have the lowest radioactivity laboratory in the world, and
Wow.
we are attracting many other experiments. There are about 10 other experiments, many of them with different techniques to look for dark matter, that are happening there. And I'm very pleased that it's resulted in Canada being one of the world leaders in what we call astroparticle physics. And many faculty members and students and postdocs working on that these days.
Well, Professor, thank you so very much for sharing your time with us today. All the best with your research. We really appreciate your words, your advice, and who knows, maybe the next Canadian Nobel laureate is watching this as a Cub or a Scout right now, as you were back in Sydney, Nova Scotia. So thank you for joining us.
Wouldn't that be nice?
And everyone at home, thank you for tuning in again. Our next episode is going to be next week, and it's going to be with another Canadian who uses their talents to the fullest in pursuit of the common good. So I can't wait for then. Thank you again, Professor, for joining us. Thank you to everybody.
My pleasure. Bye now.
Cheers.